Alright, this is this podcast 7.4, Writing and Graphing Exponential Growth Functions. Now, we have talked about linear functions before. A linear function is if you were to graph it, it forms a straight line. We talked about when things were linear functions that they have a constant change with the x's and a constant change with the y's. So if you look at this example, my x's have a constant change of positive 1. And my y's have a constant change of plus 3. So for something to be linear, you have to have an additional change, so an adding of a number to get to your next y value. Now exponential growth is a little bit different. Exponential, you are going to have a times a certain number. So your x values are still going to be constant. However, your y values are going to be times a certain number. So for example, this one is times 3 every time. And there's a certain way that we can set up an equation. We would say y equals, and this first value, we're going to call the a value, is the number for y when x is 0. So when x is 0, y was 2, so we plugged that up there. Now my b value is what you are multiplying by every time. So the exponential function will be y equals a times b squared. So we're going to write a rule for this function. So we're going to start off with, we need to have y equals a times b squared. Again, a is the number that is being represented by where x equals 0. So where x equals 0, that number is 8. So for a, I'm going to plug in 8. Now b is the value that I'm multiplying by every time with my y. So 2 to what is 4 times 2? 4 times 2 is 8. 8 times 2 is 16. 16 times 2. So that would be a times 2. And then an exponent of x. So simplify, y equals 16 to the xth power would be that exponential function. So go ahead and try to write a rule for this function. All right, letter B, we're going to graph the functions now. So to graph a function, we're still going to be plugging in values for x to solve for y, and then we're going to identify the domain and range. So the first step is to make a table. So we're going to make a table for the function y equals 5 to the x power. So I'm going to start off with plugging in -2. When I plug in -2, it would be y equals 5 to the -2 power. And we know that negative exponents go to the bottom, so it would be 1 over 5 squared, which is 1/25, which is a very, very small number. So I'm going to plot that point. I'm actually going to go by, that's 1, -1, -2. So -2, 1/25 is just above that. -1. If I were to plug in -1, it'd be y to the equals 5 to the -1 power, which equals 1 over 5. So -1, it's going to be just a little bit higher. If I plug in 0, y equals 5 to the 0 power. Anything to the 0 power is 1. So 0, let's make this, make that my 1 line, so 0, 1. If I plug in 1, y equals 5 to the first power, which is 5. So let's go 1, 2, 3, 4, 5. If I were to plug in 2, it would be y equals 5 squared, which equals 25. That's going to take me way up. So plotted my points. The second step is to draw a smooth curve through the points. I'm going to draw a smooth curve through the points. that I have selected. Now, with an exponential function like this, your graph continues to go to the left forever and ever. And it's not only going up here, but it's also going to the right forever and ever. So that means that our domain on this function is all real numbers. And my range, again, is my y values. Range are y values. So we are going to be comparing how far down the graph goes. Well, for this function, the graph is never going to cross the y is 0 line. It will get very, very close and continue to get very, very close to that line. However, it's continuously going up. So your y value is always going to be greater than 0 on this graph. All right, go ahead and try to graph this function, and then we are going to compare the graph with the graph of y equals 2 to the x power. Now y equals 2 to the x power is what is already graphed here. So compare what happens when you add the 1/3 in front of it to see how that changes the actual graph. So go ahead and do that problem. All right, now we're going to talk about exponential growth model. The exponential growth model follows a formula. The formula is y equals a times the quantity 1 plus r to the t power. Now a is representing the initial amount. So we're going to be talking about like a money factor. So the initial amount of money. R is going to be talking about the growth rate. So what is the percent that it's increasing by? And t is going to represent the time period. So let's try a problem like that. The owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. We're going to write a function that models the value of the car over time. So again, that formula is the cost equals, or y equals a times 1 plus r to the t power. A was representing the initial cost. Well, they said the value was $11,000, so I'm going to plug that in for A. 1 plus, and they said the rate was 6.9%. Now, when you're plugging it into a formula to solve, you have to switch it into decimal form. So we're going to move the decimal 2 places to the left to make it 0.069. 0.069. And the time for this particular problem, it doesn't give us a time quite yet, so we're just going to plug in C, or T, excuse me. So C equals 11,000 times the quantity 1 plus 0.069 times T. Okay. Now, Roman numeral 2 is saying the auction took place in 2004. What was the approximate value of the car at the time of the auction? Round your answer to the nearest dollar. So now they're giving us another time period. So the first time period they gave us was the owner bought it in 1984 at that cost. So the auction took place in 2004. So that would be 2004, 1984, that is 20 years. Okay, so our time is going to be 20 years. So the cost equals $11,000 times 1. It's increasing at a rate of 6.9% for 20 years. So go ahead and plug it in your calculator and solve that. And when you do, you get $41,778 when you round it to the nearest dollar. So that is how much the car would cost in 2004 if it continues to increase at the 6.9% rate. All right, now I want you to try this problem. It's very similar to the last problem. So I am going to go ahead and finish the podcast, so please pause it at this time. So this is the podcast for this section of 7.4 over exponential growth. The next section is going to be talking about exponential decay, which is a little bit different. So please make sure you remember to write this down in your ISN.